already on, right?
Yeah, this is muted. I think. Just need to unmute. Okay. Good afternoon, everyone. Well, what's this? Good afternoon, everybody. Thanks for coming to the PacTrans Distinguished Lecture. I'm Yin-Tai Wang. I'm the director of the PacTrans Center. As you know, PacTrans Center is US DOT-funded Region 10 University Transportation Center. We host the Distinguished Lecture Series once a quarter. So this year and this quarter, we're so lucky to get Professor Genda Chen coming here as our distinguished seminar speaker. Genda is a professor and IBET Distinguished Chair in Civil Engineering and Director of the Center for Intelligent Infrastructure at Missouri University of Science and Technology. I've known him for a long time. He was the Tier 1 Center Director before. And Genda is a very productive researcher. He has over 550 technical publications in structural health monitoring, structural control, computational and experimental mechanics, life cycle assessment, and deterioration mitigation of infrastructure, and multi-hazards assessment and mitigation. He has a lot of awards. I will not read everything. Most recent one is this ASCE Charles Pankow Award for Innovation. So that's a very important award. He's also a fellow of 5 professional organizations, including ASCE. Now let's welcome Professor Genda Chen for his distinguished lecture.
Thank you, Professor Wang. When Professor Wang invited me for this talk, I've been thinking about how I'm going to organize that, because we have been working on bridges, buildings, and both like drone supported or underwater unmanned vehicle supported inspections. So eventually I decided to go a little bit casual, focus on question and answer interaction session. I don't mind if you start me in the middle of my presentation, ask me a question. The only thing is that if we don't have enough time now in the end, maybe not finish that. But I don't mind if you have an urgent question to ask in the middle. And so what I did is I'm going to using the TRB presentation this back January 2026 as a framework, and then I will add other slides to make this presentation. You may see a little bit here and there incoherency, but my goal is to give you a sense of what we are doing, why we are doing, and what's so important in practice based on my perspective. And of course, if you have very technical details, I can try my best to answer you. If I'm not, I can take your question to my student and the postdoctor. You know how it goes with the professor and the student. Implementation side is requiring a lot of people to work behind. So I have fortunate to have a large team to work to support this type of opportunity with the postdoctor and the PhD student on this list. I was working with the Missouri Department of Transportation on this one. So to give you a brief summary of what I'm going to present, I put together a detailed summary here. And we will start with some objectives. And data collection is one big part of it because we develop a very unique platform. And then defect detection and quantification to condition evaluation are the key. And finally, I also briefly mentioned we also develop our own data set, because any data you collect from the internet typically is not complete, or the quality is not as good. And if you use that for decision making, oftentimes it may not be leading to good results. So we developed something, BridgeNet, and then the model optimization, and then results and validation. We did focus on 5 bridges in the state of Missouri for this work. I think all of you know the current state of this National Bridge Inventory. And we have over 600,000 bridges, but most of them are in fair condition. Nationwide are in poor condition, some of percentage. This means we have to watch this aging infrastructure more closely than before when they are new. And of course, the current visual inspection are relatively subjective, even though you give inspector a very rigorous training, you will end up with different results when they inspect the same thing. Even for the simplest bridge, single span, they study, Federal Highway Administration study, you will get a pretty diverse coverage of different answer. So if you can using machine, obviously it will give you consistent result in that sense. Obviously, instead of climbing around, certainly using a drone is more appealing in the future. So why we need automation in civil engineering? I put together 4 reasons. One is physical accessibility. And obviously you can see from the picture over here, we need a boom truck and to access different parts for inspection. There's also another part of the story. Nowadays, our nation is pushing a lot for preventative maintenance to preserve infrastructure better, so we can use the longer time, or if there's an earlier problem, we can fix that, maintain that at the early stage to save cost. So there's a washing cable, for example, early age of a bridge, and this is a result I was talking about, the simplest bridge in the world, single span, you can get a result change so much from certified inspector even. So therefore, visual inspection oftentimes is a little bit more subjective. In addition, the inspection guideline require human interact with a bridge element in some cases within half-meter distance, because they need to clean the surface or tap around the member to hear it. Sometimes you need to have that sound to distinguish one potential defect from another. So we need to create the interaction going on. Within a drone itself, you cannot interact with the infrastructure. That part definitely you cannot meet the federal regulation if you require human interaction. Certainly rating inconsistency, you can see from there, and cost efficiency is, this picture tell you everything. This is one of a bridge over Mississippi River. Underneath this bridge, they built an inspection platform. Mike from Washington know that very well. For major river crossing, oftentimes you provide that inspection platform because for future inspection and maintenance, you need that. It costs $1 million to build this platform itself. And I was joking with Missouri DOT, if they give me $1 million, I provide all the robots they need for the entire state bridge inspection. They don't need to maintain this platform either over time. They don't have to spend money. So it's really, if you do the right, robotic solution will be very efficient and effective, cost effective. So of course we do have a sort of Bible for bridge inspection, 2019 bridge element inspection, where all elements are required to have a 4 condition states assessment reporting. And if you check this definition, it often add quantifiable data, spore 1 inch or less deep or 6 inch or less diameter. Using visual inspection, looking at a certain distance is very hard to get those quantified data. So if you have the robot to interact with the bridge, that's a lot easier to get the consistent result. So all this quantified data, you can guess, but it's hard to get the decent number to fulfill the requirement of this regulation. So of course, there's another issue with manual inspection. Even to record all this information from one bridge itself is also an effort. Manual recording is also a significant effort, especially for the bridge where you have difficult to access area. It will be awkward for you to even record things on the way. If you have a bridge, you have to climb somewhere. So all this, if you can generate with the machine, you can automate the process. It will be very efficient. So our solution is the automated inspection, mainly 4 steps: data collection, defect detection, quantification, and the condition assessment. So we will go through each step in this presentation, but I encourage you, you ask questions so I can always elaborate more when there's unclear remarks. So obviously we will use the unmanned area system, combining drone, climbing robot, and the sensing system to make the inspection more quantitative and systematic in that sense. We can improving also automation, not only that, but also safety for inspector. Yeah, because you are working on ground instead of climbing, hanging somewhere on the bridges itself. And so that's the difference for automated solution. Again, to give you a little bit more detail for each step, and you can see obviously easily understand different steps. So these are the 3 step and 4 step is the key part of this presentation. Basically, it's easy to understand using UAS to collect data, and then using automatic extract video frame using AI. And I'm going to show you some slides. And then segment both bridge element and defect from multitask machine learning. Because when you're using a drone or our robot, you collect tons of video and the data. Asking engineers sitting in front of computer to sift through those images is impossible, and they're very boring also. So it's not good use of time. So instead, this is a perfect opportunity to ask AI to pick out, let's say, 50 to 100 frames from 2 or 3 hours of video. So engineer can only evaluate this 50 or 100 frames for interesting feature. That will be ideal. So in that case, even the AI does not have to provide you very accurate result. As long as you pick up the most interesting part for engineer to review, will be fine. So that's a good use of AI for that. And then to quantify that, obviously, this is another part. Using visual inspection is very difficult to quantify them, especially as a remote access. So using the digital technology, we can quantify the dimension and the size of a defect. It's relatively easy. Sometimes you have to do 3D reconstruction, which takes some effort, but typically, once you develop a 3D, you do not have to redo that every time. So you just need to do that once, for example. And then, of course, we will compare whatever image we collect, compare with the 2019 manual for bridge element inspection, and we can use in graphical comparison or other comparison to determine the condition state much better than just a human look at the bridge and say condition state 3 or 4 in that sense. Because you can quantify the correlation between what you see on the actual bridge and what people put into the guideline as a reference in that sense. By talking about that, there's also opportunity. We can also evaluate whether the image put in the 2019 manual are reasonable or not. Because those are picked in ad hoc way, sort of arbitrary way also, but they may not be so scientific, even though we put the category 1, 2, 3, 4. So we have also a set of a commercial drone we acquire, and some of this, the last one we actually developed specifically, and then ask a vendor to build for us only. So we have a suite of a commercial drone. These are nothing new, but we use the Skydio 2 and the Helios 3 quite a bit. This is made in the US, and that's made in, I believe, in Europe, the country is Sweden, I think. So these are 2, and we use the DJI drone quite a bit as well, but moving from last year, we began to use the DJI drone less and less because some clients, they specifically ask us not to use the DJI drone. So that's another reason. But we focus on our own robot system. As I said, the commercial drone does not give you an interactive feature with the bridges. And some of this feature interaction with a human hand are required in future inspection. So the only way we can satisfy the federal regulation is create a robot, enable us to interact with the bridge directly. And we do that by creating in two senses. I'm going to jump into this one first. For example, this drone can fly to underneath the bridge girder and then grab the girder and then just hanging on there like a driving vehicle. And I'll show you a video very soon. Once you engage with the girder, this is no longer a flying vehicle. You can turn off the propeller and then just moving, traverse linearly. So when you do that, there's a lot of benefit. And first benefit is, the most important benefit is no longer than commercial flying around. You will be sometimes moving around because of wind or whatever reason, or the illumination light condition is not consistent. You have a shadow, you have other. Once you engage here, all those problems are gone. So the data we collect is a very, very high quality, consistent in that sense. Okay? But more importantly, this guy can carry a palm-sized crawler, like this one. This can carry by this one. Once you engage on the girder, this can launch this one off to the girder, and this guy can move around on the surface of a structure member to inspect corroded area, connection area, bone, or other whatever feature you are interested in. So this together can cover almost every area you are interested to inspect. That's the purpose. And this can only do not only the visual inspection using camera, can also do the non-destructive testing. This is a testing of this ultrasonic velocity tester for metal thickness measurement. And this is a probe. And we also have underwater fully submerged robot, ROV. We also have a surface water vessel to carry sonar underneath to survey the bridge scour problem area as well. And this is one we developed our own drone with a magnetometer to communicate with so-called smart rock. The concept of smart rock is a sensor put inside the concrete ball, and you deploy this concrete ball near the bridge pier where the bridge scour potentially happening. As the bridge scour happening, creating a hole more and more, this smart rock will roll into the bottom of the hole. By communicating from the drone, like 5 or 6 feet above water, with the smart rock, we can identify the location of smart rock in real time, even during flood season, where you cannot send diver to do any inspection. We can use in this. In 10 minutes, we can collect all the data we need to assess whether your scour hole is increasing or not. And that data is very critical for DOT to make a decision during the flood season, for example. So we do have a combination of area underwater vehicle, structure crawler, and the hybrid vehicle. And I'm going to show you some video pretty soon. Luckily, like Professor Wang mentioned, we did won 2025 AAC Charles Panko Award for Innovation for this one. And they quote, "This is truly revolutionizing bridge inspection in an automated way, leveraging AI and the drone technology." So you can see this is what we submit to AAC actually. This is the more finishing product hanging, and then this inspection, you can launch the crawler for this real in-service bridge. For inspection, you can automatically, in real time, display the thickness of the metal, like a girder wet side, as the crawler moving around. And you can also see visually the surface peeling of the coating area. And all this can be quantified automatic way if you do that. And this is an image I just received from Inhai yesterday. So I put that. That's where US DOT presentation I've been making, the impact of a robotic solution. Now, you may ask, why hybrid robot? I summarize here, increasing operation time. Flying versus traversing, the time, like consumption of battery power is in different order. if I can fly 10 minutes, I can use that same power to traverse for more than 1 hour. So this will make these technologies more practical for addressing real civil engineering inspection using crawling and flying capability together. Second one, as I mentioned, you can create a measurement station. It's very robust. Third one is easy in navigation because instead of flying 2D or 3D, we are flying in 1D basically, moving 1D. And we also can accurate the positioning because even if you are familiar with a survey wheel, right? If you walk around, you can measure the distance from beginning to wherever you are. We can use low-tech surveying wheel to measure the distance from end of a girder to wherever you are inspecting. That way for DOT, it's easy to use that. Forget about the GIS and other referencing where you have to learn, especially by using, say, the distance from Pier 3 to this inspection location in 20 feet, any bridge engineer will easily know that. So it's easy to connect with practice as well. These are the two mechanisms we created, mechanical and magnetic engaging mechanism. The one I showed earlier in picture is mechanical engagement. This is good for both concrete and the steel girder. And this is a magnetic wheel is good for steel girder, obviously. So I will show you a video pretty soon, but this is another summary of this one you saw already. I showed you, but this is how this the initial standby position. This is operation, non-destruct testing, and this is a control system we have. And we also have another crawler using magnification. Like this is called like a mini camera. You can magnify the things for 500 times, 1,000 times. So you can do visual inspection remotely, basically. So if I give you the video, you will see. So first of all, the engagement with a drone with the girder, and this is a real bridge in the state of Missouri, flying to engagement to this girder at the bottom flange, and then from there I just moving around in one dimension. When you turn off the propeller, it can save a lot of power. Okay. The second one we tested on the river crossing bridge, cable stay bridge. So you see the launch this crawler, and then you can see moving around to, and it can carry the camera. I'm using another Skydio 2 drone to shoot for this video. So this can also see the Skydio 2 occasionally. So you can move around to different part of the bridge. If you are interested to collect more data in certain area, you can just move over there. And then very soon you will launch the probe I was talking about to measure the thickness. This is ultrasonic technology. You can show directly on the screen whatever the measurement you have, you can show in real time as you go. Yeah, so that's basically if you want to take a quick look again, so because this is one of the unique capability we introduced. At the time we began to work on the bridge, this is the only one in the world we can do it, actually. So that's why we got the patent, we got the AAC award, basically, on this technology. So, and again, one of our goal is to push this technology for inspection of a long span bridge. Because if it's crossing over water, it's a lot more challenge to inspect. It's manually. And these things, it doesn't make a lot of difference, whether it's on land or over water. So it's a very, very relevant to bridge inspection in this sense. So this is a one showing the highway bridge and the river crossing bridge. The next one, I also want to show you the real-time well inspection capability as well. But before I do that, I was showing you, instead, we're also involving one of a manual inspection on the real river crossing bridge. This is my team does all this non-destructive testing manually on the pier. So in the future, we hope we are actually begin to work on this, create a water surface vessel that can do all this automatic way instead of sending people to the river, the middle of the river to do this. As a matter of fact, the water the challenge is water is always moving so much. So we have to take advantage of this control technology, and then also create a creative way to make sure the non-destructive testing part is stable. Otherwise, you cannot get the nice measurement in that sense. So that's what we got some experience from the field operation with our clients. So this video is showing you one of this is for well floor detection, and this is the demonstration in the lab with the metal structure member. And then it does take a little bit of momentum because the crawler has a certain weight, so you need to move a little bit of speed to get over the gravity effect. So you can see we have prepared the well specimen. As it moves, you can provide a real-time detection of well is a cracking or debonding or cavity in the well. And of course, this is a pre-trained AI built into the robot. So once you take a new image, you can automatically speed up. You have this is a crack at the confidence level 75% or whatever you have. If you are working on AI, you know this is based on instant segmentation. You only have a confidence level. You do not have accuracy because you do not have ground truth to compare in that sense, right? So if you're working on that, you know that. And then, especially this quality is good in the crowded area. You can never send people in. So this is a river crossing bridge at the anchorage area. There's no way you can send any engineer close by. But this guy can go anywhere. And so it'll show you in this video very soon at the last part. And you can see this, if you want to see if there is an egg in the bird nest, you can also see that using this. Yeah. So this technology itself is very good. Of course, it takes engineer to plan for the mission and to do some meaningful task. Yeah. But these are just a tool, just like AI and robot, they are all tools. Yeah. So we have to make a good use of that. And so this I started showing you some live feedback. You can see the fine grain of the texture on the surface. This camera we put on, it was a 500 times magnification factor. So you can see very detailed. So for PhD work, the value is not how to build this thing. The value is how to use the data, or you're planning for the task and then use the data. These are the real value you have for PhD work. Yeah. So it took me, my research engineer and postdoc, a lot of time to design this unique robot example. But I never asked my PhD students to do that because they have a firm deadline for graduation. You have to publish the paper, for example. So this is a retrieve of the crawler, you can see, and this is probably going to the anchorage area. You can see, yes, a very tiny space they are walking on. Yeah. And to the anchorage area very soon. Yeah, this is going to the anchorage area. You can see here, it's actually tiny space over there. And it's all kind of a jungle over there. And so, but this guy can go anywhere, even between two stiffener over here, and you can never see it. They can send back the real-time image, actually. See, go between the stiffener. So you cannot see the crawler itself visually even. So we basically demonstrate this really nice tool for us to, yes?
How do you control it at that point? What's controlling it so that you can get it in between the two stiffeners?
Have you ever played video game?
No.
This is just like a video game. I'm sure your kids will play this one, operate this very much.
Okay, so you've got a camera and you're just,
Yeah, we just control the video game basically. Okay. Yeah, we have a feedback, live feed of the video. And so
So what's the communication range?
So we didn't test to quantify that yet, but the one we typically within 1 kilometer is not a problem. So we didn't test the extreme of what are the maximum distance yet. That's something I hope we will test on the real application case. The current technology about this local Wi-Fi is 1 kilometer is not that challenge. So certainly, I guess if you have an intermediate block, it may interfere a little bit, but we tested over many buildings. Even 1 kilometer is not the issue. We can still make it work, and even beyond the visual line of sight. But we haven't formally quantified that yet.
So which protocol did you use for the communication?
That will be my team member probably have a better answer for you. I think I leave my student probably I can answer find out for you, but if you're interested. So that's I don't want to give you the wrong one. So we test a few of them. For example, we're using LoRa. You're probably familiar with LoRa, right?
Yeah.
We're using that. Also, we test that can reach to 1.7 mile range, not a problem. And if we have to go farther away, we will have to use an amplifier. Yeah. So I think current wireless technology within kilometer is not a major challenge anymore. So LoRa is one device kind of technology we use, but we're also using others. So this is showing you a video like a solution with a big crawler. This crawler is 40 pounds actually. It's pretty heavy. You can carry a decent computer inside there if you want to, with a lot of power, real-time processing power. But this can show you all the detailed image from this movement at the connection area. So let's try one more time. So you can see the peeling off the paint. Mike, we're talking about quantify the coated area, the deterioration. With this information, we can easily automate the process to quantify them, basically. Yeah. And you can see the quality we did is so well. If you fly a drone at the 6 feet away, because of they are oftentimes hiding behind something, you have different level of light illumination. The quality, I guarantee, is not as good as this. So the next step is that we have to detect the defect. And as I mentioned, we're using AI to do this job. In particular, we develop a multitask AI, which meaning we detect the type of element, bearing, back, abutment, and the defect, type of defect, crack or corrosion area at the same time. The benefit to do multitasking is to enable you get a well-performed AI much faster, much more robustly, and also more accurate in a sense. Because the AI can take the information from element and defect in some correlative way once you train that together. So that is helpful. And so for example, we do have to have, this is a frame, this is an element ground truth, we label, this is label for element, this is a label for crack, or this is a crack, basically. So you have to do part of labeling, you know that. And my student did almost 7,000 images in the database. We created a BridgeNet to do this work. And then further on, we talk about the element, barrier, bearing, back, superstructure, substructure. They are all terminology in the 2019 manual for bridge element inspection. Okay, and then for defect is corrosion-like or crack-like. This is something I also appreciate that Mike was mentioned this morning. Machine doesn't differentiate spider web and crack. Okay. It's a human have to do the job. That's why you cannot trust the AI 100% in many cases. You have to know what's going on. So one way to differentiate is your remote sensing can differentiate that. Because, for example, here, this is a hyperspectral imaging. By the way, if you never heard of hyperspectral imaging, it's an extension of RGB camera. Instead of a 3-channel, here we have hundreds or thousands channel, basically. So you can see beyond what your eye can see using hyperspectral camera. The good thing with a hyperspectral camera, you can tell the difference between different materials. Here you have a middle, like yellow painting. Here you have in the middle of a dark. Here you have some stain, or here you have a white mark. Here you have vegetation, or steel guardrail. All these come with a different spectrum. Therefore, you can use this technology to identify different type of material on the surface scene. But you can also using the thermal imaging to differentiate something. What thermal camera cannot differentiate whether you have a crack or construction joint. It's the same way to see the contrast of the thermal. But if you combine this one with this one, you can certainly differentiate that. So you can use technology to differentiate to make sure there's no confusion with that. Crack light or crack is different. Okay? And then, of course, to use some improve the model robustness, data augmentation, and also class imbalance is always a problem for civil infrastructure because for in-service infrastructure, we are always biased to the no damage case than damage case, right? We know because otherwise your bridge will not be in service. So how to address that to make full use of limited data is always a question in civil infrastructure. So we introduced a weighted way to make this balance in somehow, even though you're using imbalanced data. And that will give us a more benefit down the road. And this is an architecture for this multitask defect and element. So there's a crosstalk in the middle. So there's an enhanced capability of what we're doing. So this is for bridge, element, and defect identification simultaneously. So this is a predicted area versus the ground truth. If you can compare, this is the image from the camera directly. This is the ground truth we label. And this is using the more like original commercially available multitask training learning using high resolution map. And this is the one we're using weighted average. So you can see the result is much better than this one compared with the ground truth. Because we are addressing inevitable imbalanced data set in this way, okay? So the other way to look at that is, and I mentioned the weighted information already, and then element segmentation typically is a lot more accurate than the defect because element is large surface and more to cover easily. So if you have a crack, it's only tiny bit, for example, it's a lot more challenge. It's depending on how much data you have also. So overall, we have element about 95%, and the defect crack or level is only 65% from this study. With the more and more data you put in, you can enhance the prediction. That's what database or data-driven technique is about. You need more data. Okay, now the other practical issue is, I mentioned to Mike this morning, bridge, same type of bridge in Washington and California, they may have a tiny bit difference. Although overall you have still got a bridge. We call the same name. So how to use the trained AI in Washington state bridges for California bridge evaluation is actually a practical question to ask. So we're using domain adaptation technique to help bridge the gap between states. What does that mean is if you train AI in the state of Washington already, you do not have to label California bridge of similar type bridge anymore. We can using AI itself to help us self-correct the difference between the two states and then predict the element and the defect at the same time. So this is a domain adaptation technique. We developed this based on the histogram matching technique. And the idea behind that is, for example, this is a Virginia Bridge is a source domain. We have a fully labeled data. And this is, let's say, Wisconsin Bridge. It's similar, still good a bridge, but it can give you quite a bit of different feature here and there. Could be the coating they use are different. Okay, different color or different chemical could be different. But you can do a minimum work without labeling Wisconsin Bridge to make this AI trained on Virginia Bridge work. The way we did is, okay, we take some representative patch of image and compare the some representative patch here to analyze their color distribution and make them match so we can create, for this bridge, the equivalent the bridge will be this, not this one. So we can augment the bridge image by this way, and using this, the same labeled one before, you don't need to recreate the labeling. And if you add these two as a training pair, you will be able to adjust the prediction of this one. That's what we do with mixed, because this part you do not need to have a supervised. We don't need to label. This part you do need to supervise with label. Okay? This mix has a minimum effort to achieve the extended service for bridge element and defect detection. That's the concept behind that. Now, how effective it is, and this is how we implement this. You basically, instead of a traditional one, you have image label data, you have a segmentation loss minimized to create the AI model, right? You add another one, so-called adversarial loss. The idea is to ask the AI, okay, while you are predicting this bridge, at the same time, you can minimize the difference between Virginia Bridge and the Wisconsin Bridge through this adversarial loss at the same time. Here, you do not need to have additional label data. So it's a minimum effort you can do to achieve that. How effective it is, and this is what we call class-wise histogram matching, UDA. So HMUDA is our approach. And there's a conventional UDA in the computer science community. Or if you compare with without doing UDA, so this is actually original one. You can only reach like a 51%. If you do the conventional UDA technique, you can have 63%. But this is what we come in with our technique. So for this, if you're working at AI, you know intersection of union and precision and recall, right? They're all measure of accuracy in a sense, right? So you can see consistently our approach can reach very high because of this histogram matching technique we introduced for domain adaptation. Okay, so defect measurement is nothing is quick. Elia 3, if you're ever using that drone, they come with a software so-called inspector, allow you to do some quantitative measurement from image like this, but it's only some image you can do. When you have the image perspective camera to the structure member almost perpendicular, you can get that measurement. If you have 45 degrees, you cannot get any information because the automatic measurement distance is not so accurate. They didn't provide you. It's because Elia 3 carry a LiDAR together with RGB, so you can measure the distance. Okay, that's one you can see that. But the other way to do that is the structure from motion. You're all probably familiar if you're working on the AI things. You create a 3D reconstruction of a bridge based on two-dimensional image, basically. That's how we. So for example, here is a tight spot point, which means if you fly several times, you're trying to put them together. And that's one of the most challenging tasks. For building, like computer science people always publish paper on building interior situation. It's easier because there's no setback, there's no limited occlusion. For bridge, there's a lot of element hiding behind another element. The lighting situation is totally different. It's a lot more challenge, believe me. So we spend a lot of time. So even though you have a two fly, you're trying to find the common point, both fly involving. And if you pull those points out, you will have a spot point cloud like this. So once you have those points, you can back calculate the pose of a camera. Once you know the pose of camera, you can reproject in much denser image on the 3D. And then once you combine with the 2D camera image, you can get a complete finalized texture, like original real world. This is like a replica of the real world. You can inspect this anywhere, from any time, anywhere, by anyone in the future. Okay? With that one, these are basics for digital twin in the future, basically. It's the 3D construction. Now, this is another one. We can integrate, fuse the LiDAR data with RGB data, even enable us to measure, because LiDAR data come with a three-dimensional georeference information, so you can measure any time, any distance on the surface. We haven't shown you the clean up surface like RGB texture with the measurement yet here, but to show you the concept, by merging the LiDAR point with RGB, you can not only knowing the texture on the surface, but also measure the surface distance. Okay. Here is a comparison of the accuracy of this measurement. Is very accurate, 3%. And condition assessment, finally you compare with the specification. This is an image from specification. We compare certain area, compare this image, you make a decision, and that's more quantifiable than the totally subjective, human call it based on the visual image. So this is a measurement of a size. Sometimes Inspector software doesn't work. And so this is a quick summary of, of this presentation. We have a 4-step automated approach. It's very promising for bridge inspection. The workflow makes assessment faster and more objective compared to current visual inspection. The combination of multitask AI and structure from motion 3D modeling provide very robust solution for defect detection and quantification. In the future, we would like to improve a little more, actually, based on what we are doing. Actually, this was starting last year. We are already working on this. And then I have to thank the US DOT, even though the grant finished last year, it still trickle down the technology we have developed in the past 8 years. We also have a proof of study from 7 states to support this work. With that, I can answer all the questions you have.
Thank you. Any questions?
It's good I didn't add more about scouting, because otherwise we're running out of time. Anyway, yes, go ahead.
So the system, first, thank you so much for this great presentation. We learned a lot from that. That was awesome. My first question is that does this technology is generalizable to the concrete structures also? Like,
I was showing Mike a picture. We have this hanging drone on concrete girder. Because it's a mechanical clamp, it's the same. You just need to have some tailor to that concrete situation. But yeah, most of the time we spend on the steel bridge, but it's the same concept. We demonstrate on the concrete girder also.
okay, awesome.
Now, of course, in that case, you cannot send that crawler with a magnetic crawler. But there is also another type of crawler based on vacuum.
Yeah,
You can
suction.
do that. On the personal level, our UTC actually developed that one also with the City College of New York. But on my personal opinion, in the future, I'm not developing further the crawler for concrete structure. Because you know the difference between concrete structure and the steel structure? Concrete usually is dealing with large surface area.
Yes.
That's where you use concrete the most efficient. If you have a complex geometry like a steel girder, it's not efficient using concrete anyway. You hardly see that complexity like a steel girder for concrete girder. So if I'm dealing with a concrete girder, I find it's a lot more efficient just using drone itself. We actually haven't shown you yet. We have a drone with 1 or 2 robotic arm on the drone itself. You can do the interactive work on concrete surface more efficient than crawler. Because rely on vacuum to crawling on the surface of concrete, sometimes it's not efficient, especially if you have a void here and there. Concrete, often see you have uneven surface. It's not that efficient. to manage the mechanism. Okay, it's not so safe to make sure it's on the surface. That's my point.
Thank you.
That's why I say in the future we are not developing concrete surface crawler for that reason. Okay.
Any other questions?
We are all learning from working experience.
Thank you for your great presentation. Just kind of interested in the parts on your presentation. You said you're going to collect the data, the 3D mesh stuff, right? You're going to reprojections, trying to build a digital twin. Just curious, are those or like processing on the edge side, or are you going to, do on the server?
So the one I'm presenting to you is not on edge device.
Mm-hmm.
But if you want to process the digital twin on edge device, the first thing you need to check is storage and the CPU power, GPU. Because processing for digital twin, depending on size of your system, it takes a lot of data and storage. So for example, when we develop the whole entire campus digital twin, it's hard to put the high resolution on the edge devices. But you could do this way, modularize the digital twin. For example, for this span, you would like to have a digital twin put on the edge, even on the robot, carry an edge computer. You can do things if you want to. It's depending on the storage and the GPU power, how much you can do basically. But in terms of technology, there's no difference. It's a matter of GPU and storage capability, basically.
Any other questions?
Yeah,
Jeff.
Oh, nice. Thanks for the great talk. So I have a question about the weld fracture detection and weld defect detection. What's the size? You must have been training something to be detecting those failures. What's the size of the training data set? What kind of different conditions? Because it's like super sensitive to lighting, to all of these things.
So in addition to what I'm showing you about the weld specimen here, but I also working with a company in German City. They are providing steel girder for 22 state DOT, and I haven't included that. I haven't included that data yet, but they build a real, as realistic as it can, full size of girder for us actually. We have a 6 feet long, 20 feet flange width, and then 1 inch thick is a good, strong girder.
Yeah.
And they create it's all realistic. So they are asking us to develop a technique for automatic inspect the weld in factory actually.
Okay.
So the way currently our understanding based on, in that case, we're using laser profiling. It's not using the camera view itself.
Okay.
So is it doable to the realistic size of weld defect? We can pick it up using the sensing technology. So it's a matter of how stable your station to collect data. Okay, obviously, if the station itself is moving around like a drone, I'm sure it will be very challenging to make it work. But with a crawler, you can, because we can even stop to collect data. You can imagine. So it's a perfect stable station, and that enables us to do that. So, but for the specimen we prepare in this presentation, our technician in the department create that. We have debonding. For example, you have between weld and the parent metal, you have a little bit debonding tiny. You cannot even see sometimes using eye, but if you position the camera in the right angle, you will be able to see it. Yeah. And we can pick up the crack tiny bit, just like a real crack, because we actually add some stress to create those crack, like a real crack. And cavity is easy. Cavity is a lot easier because they are typically bigger. Yeah. So, in my view, I think it's doable with a practical problem using the current technology now on the crawler. Yeah, not on the drone flying around.
Yeah. Thank you.
Yeah.
So given the time constraint, I have to take the opportunity to ask the last question.
Sure.
So we have a very aged infrastructure nationwide, right? So you see this kind of bridge collapse almost every year.
Right.
So this technology, I think, is definitely very useful. But I was thinking like the crawler design, is pretty challenging, right? It will be applicable to steel bridge, but it may not be useful for the concrete bridge at this point.
Right. So as I said, I will not, from this point on, I will not spend time to develop a crawler for concrete structure.
Mm-hmm.
We are actually working on drone itself.
Yeah.
A drone with a robotic arm is a lot more efficient than crawler on concrete surface, because you are dealing with a large surface on concrete typically. So we can fly a drone using lateral connection with the girder to do the interactive activities more effective than crawler. Besides, crawler moving speed is a lot slower than drone. If you have a large infrastructure, you also take a lot of time from point A to point B. That's why our technique to relay operation from fly traversing to crawling is effective for large scale infrastructure, because we can fly to certain area and launch the crawler. Instead of a crawler from A to B take many hours, it's not practical. So for concrete surface, I advise my team to go with interactive drone instead of a crawler anymore.
Yeah.
Because the first 3 years our UTC tried with that technology, although there is some success, but there's still a lot of challenge. As I say, maintain the airstream to attach to the surface of concrete is not trivial. Yeah. So
that's wonderful. I definitely believe the combination of the drones and the crawler is going to be covering every kind of bridge. So one other recommendation I can provide is actually the data communication is also a huge a burden, right? So if you send every image back, so if you do a lot of edge computing, right, on the device, you only send the image with the potential defect.
Right.
I think that will also save a lot of communication.
That's something, that's what we are moving forward, actually. So now we have a technique, we can certainly do AI processing on the crawler itself, and then sending back just critical information. You don't need to send back 2 hours of video, you just send in 50 frames to the engineer. That will relieve the burden of this communication. Yes, definitely. That's
okay. I know this is a very interesting topic, and Professor Chen will still be available actually about 30 minutes after this, but our seminar actually is scheduled until 3, and I have a class to teach too at 3. So let's give him a big round of applause, and you can stay around to talk with him if needed. Thank you very much.